Then we should do a share screen. Share. Oh, it works. This would be number 22. Okay. So what I want to do, we have to finish the discussion about quantum chromodynamics, and I want to do a tutorial. And since it's kind of difficult for me to tell how long the tutorial is going to be, then I prefer to start with the tutorial because I want to finish it today, so that we will. I'll give you the next problem set today. As I told you last time, I want to give you from now on a problem set every week in the last 3 weeks that we have left. So so that you have more things to practice before the exam. Another thing is that I got an email, I guess you got it as well, possibly, about the student evaluation form. So as you know, in Bar Ilan, we ask all the students to write down what you think about the teaching of H1, including this course, of course. So please go ahead and write your opinion. This is very helpful, helpful to improve. And of course, if there are things that you like, of course, say them. If there are things that need to be improved, please say them as well. That's about that. Okay. Any questions or comments before we start? None? Okay, so we're going to do a tutorial now first. So as I said, we're going to start with a tutorial. And the tutorial is going to be about weak interaction, conservation laws, and addition of angular momentum, because as you saw, we're going to need that. So I just want to make sure that you're all aligned with me on that. A thing which you are supposed to know, but some of you may have different backgrounds, so I cannot be fully certain that you're all aware of these things. So the tutorial today is going to be about the weak interactions, conservation laws, and addition of angular momentum. I think some things here are things we already discussed or things that you're supposed to know already, so we'll go relatively quickly over them, and other things that might require a little bit more careful considerations. So we saw that the weak interaction, I'm going to have some thorough discussion about the weak interaction once we're going to finish the discussion about the QCD Lagrangian. The weak interaction has some very interesting properties, which makes it different than all other interactions, the electromagnetic and the strong. And here we're simply going to learn a few more properties of the weak interaction. So similar to the electromagnetic interaction, right? The weak interaction is mediated by spin 1 boson, the gauge bosons. But unlike the electromagnetic interaction, which is mediated by massless photons or massless gluons in the case of strong interaction, the bosons that carry weak interaction are massive. So the weak interaction is carried by massive gauge bosons. Right, we have the W plus minus, which carry charge. So they carry the charged weak interaction. And their masses are around 80 GeV. And the Z boson, which is neutral, interaction, somewhat heavier. The mass of the Z boson is 91 GeV, roughly. Now, as we said, all fermions take part in the weak interaction, and neutrinos interact only via the weak interaction, nothing else. Right, all fermions weak interaction, and then the neutrinos interact only. I don't need that. What do you want? How can I? Well, how do I get rid of this one? Oh, like that. Neutrinos interact only via the weak interaction. Now, since the W carry electromagnetic charge, right, then they connect in vertices between up-type quarks and down-type quarks, right? So W plus minus carry charge means that they connect, Q up, charm top, and the Q down, right? Down, strange, bottom. Or a charge in neutral lepton. Right, because electromagnetic charge is conserved, right? So if you have a, let's say W plus, right, it would connect up type quark and down type anti-quark. Right, or up type quark could turn into a down type quark in the W. Or a charged anti-lepton would connect with an anti-neutrino and a W. Right? With the charge W, because remember, this is something which some of you got confused for some reason. Charge is conserved in every vertex. Now, as we saw last tutorial, the W plus minus connect quarks from different generations, right? But there is a smaller probability, which is given by this CKM matrix. W plus minus connect quarks from different generations. So it's lower probability. But that's true only for quarks, right? So the lower probability means that the smaller coupling constant. Right? Then same generation quarks. Right? Now we don't have that for leptons. Right? For leptons, there is no mixing between the generations. For leptons, There's no mixing between generation. Yeah. Right. So the way we described it was with the CKM matrix, right? We said that we can think of it as a different coupling constant. So we can say the coupling constant, you can call it, G weak for the leptons and G weak Vij for the quarks. And Vij, which is the VCKM, right? Kabibo, Kobayashi, Moskawa. We gave it last time. I just repeat the number: 0.974, 0.225, 0.004, 0.225, 0.973, 0.041, 0.009, 0.040, and 0.999. Right, so really it tells you what are the coupling between the different generations. Right, so if you see, top quark, right, quarks from the 3rd generation would nearly 100% would interact with quarks of the 3rd generation. But there is some chance of interacting, let's say, top quark with a strange quark, right? Or a top down quark with a down quark. It's also quite small. It's less than 1%, but it still can happen. Right? So still 99.9% of the interactions of the top quark will be with the bottom quark. But there is this coupling. Right? Now, this is only true for the charge currents, right? The vertices that contain the Z0 boson, right, the neutral current, conserves the flavors. We don't see in nature anything that makes generations from different flavors with the Z0 boson. So vertices that contain a Z0 boson conserve flavor. So we said that the technical term is that there is no flavor changing neutral current. F, C, and C. Observed in nature. Right. So it's not part of the standard model. Maybe it's part of more, extensions, but not part of the standard model. The vertices that involve the Z boson are similar to those of a photon, right? There's one exception, as we said, that neutrinos only interact via the weak interaction. So there are vertices that of the Z boson that involve neutrinos. But neutrinos can only couple to the Z or to the W bosons. Right? So generally, the vertices with the boson similar to that of photons. Vertices with Z boson or similar to those with photons. And so, for example, we can have anti-quark or anti-lepton interacting, quark and anti-lepton, and interacting via the Z0 or via the gamma. So we can have a Z and a gamma producing a pair of quark, anti-quark, or lepton, anti-lepton. These are things that we see in nature, right? For the neutrinos, we don't see interaction via photons. Right? They only interact via the weak interaction. So for neutrinos, right? So we have the anti-neutrino. What did I do? Oh, just switch the order. You can have a Z boson or the neutrino, anti-neutrino. Made some mistake here. Now I'll just mention, we haven't had time to do it, right? In quantum chromodynamics, I said that well, I didn't say, right? Gluons do carry the color charge, and that means that they can interact with each other. Similarly, in the weak interaction, the W plus minus and the Z, they carry the weak charge. W plus minus and Z carry the weak charge. W plus minus, of course, also carry the electromagnetic charge. Right? Which means that they can have self-interactions between them. Right? So we can have something like, I don't know, a Z, right? Z boson that interact and produce a W minus W plus. Right? Same is true for the photon, right? You can have a photon that produces a W minus and W plus. We can also have self-interactions between them. So we can have something like a, W plus, W minus interacting, produce another pair of W plus and W minus, or W plus and W minus interacting and producing a Z0, Z0. This can also happen. You can also have Z0 and a gamma interacting to produce a W plus and W minus. It's true for two photons as well. Gamma, gamma can produce a W plus, W minus. This all can happen. We're not going to speak about those because we don't really have time. Just that you know that these exist. All right. I will show you how the gluons interact with each other, because that's part of the QCD, and that's kind of a continuation of what we did on Tuesday. But I won't go deeper into that because I simply don't have time.
You have here vertices with 4 bosons, right?
Yeah.
I thought we said that we allow only for 3 at a time.
No, I never said that.
So that was only an example in the former models, but not a general restriction?
Yeah.
Thanks.
I also have a question about these diagrams. The first one,
yeah.
Doesn't that violate energy momentum?
No.
Because I mean, it says 0 is at rest.
There is no rest. No, it is not.
No, they can be virtual. They can be just a part of that. Another
virtual, of course. Of course, they're virtual.
Oh, you think it's just, you're saying there's just a vertex inside a larger diagram. It's not.
Yeah, of course.
Okay.
Of course, you don't see the by that way. It's a gauge boson. You only see it as part of something bigger.
Okay.
Okay. You don't see the bosons hanging out. One comment about the strength of the interaction. So the fact is that the weak interaction is only weak at low energies, right? So it's the weak interaction. It's in fact much stronger than the electromagnetic interaction. It is only weak, right, compared to the electromagnetic interaction. at low energies. Right. And of course, the reason is the masses of the W and Z boson, right? Because, you know, the way to see that, this is due to the masses, to the large masses, heavy masses. The W and Z. Right. Remember that every propagator in the Feynman diagram, right, has a contribution. What's a contribution? Yeah, guys. Can you hear me?
Yes, we can. Is it 1 over p squared plus m squared?
Nearly. It's I over q squared minus m squared. Right? Right. M is the mass of the propagator, right? And q is the momentum, right? We had something like two particles interacting, right? P1, P2, and then we had a propagator, or gamma, right? Momentum Q. And then we had P3 and P4, right? Remember that? We were discussing that. That's a way of describing an interaction, right? So Q is the momentum transfer. M is the mass of the propagator, right? M, mass, and Q is the momentum. Momentum transfer, right? This is a transfer, right? Change in momentum in the vertex. Right? If we had an S diagram, then Q is P1 plus P2, right? The center of mass energy. Right? S diagram, meaning that Q squared is P1 plus P2. Squared is center of mass energy. Right? I'm not telling you any news. So, what do we have at low energies? What do you mean by low energies, right? Low energies, meaning what? What is low energy here? Right, guys. When I say low energy, what do I mean by low energy? Oh, come on. Somebody help?
The Q is small, right?
Q is small with respect to what?
The mass.
Of course, right? Low energy simply means that Q squared is much smaller than mz squared. Right? This is low energy. Right? Q is less than 90 GeV. Right? So if I compare a diagram with the weak force and the diagram with the electromagnetic force, which is mediated by the photon, right? So for this, we have 1 over q squared minus mz squared, right? Squared. Right? Q is much smaller than mz, so it's 1 over mz squared. And then the electromagnetic, corresponding electromagnetic interaction. right? You have 1 over q squared. Right? Q here is the coupling, right? So we have suppression of the weak interaction by a factor of q over mz to q is the momentum, not the coupling. Q over mz to the power 4, right? Which is quite weak. But of course, at high energies, right? Q squared is much greater than mz squared. Then 1 over q squared minus mz squared is 1 over q squared. And then the mass of the boson becomes irrelevant, right? And the electromagnetic and weak diagrams are comparable, right? And that is indeed what we're seeing, right? Because the coupling constant, and then EM and weak interactions are comparable. Right? Alpha weak, I think we discussed that. G weak squared divided by 4 pi is approximately 1 over 30. Right? And alpha EM, what is alpha EM? How much is that?
1 over 137?
Yeah, very good. Factor of 4 difference. Actually, the weak becomes stronger. So it's really weak at low energies because the masses of the W and Z bosons are so heavy. Now I'll describe to you the Higgs mechanism that gives the masses to the particles. But the fact is that these are the exact value of the mass is determined in the standard model. It's something which you get as a free parameter. This is nature given. Right? Questions about that? No? No. Then another thing to, okay, a few more things to say. Helicity. So we discussed helicity. Just want to do a quick recap of a few things. So when we have a free particle which moves at constant momentum p, a free particle, momentum is p, then the projection of the spin s on the direction of motion is called the helicity. Lambda is defined as s dot p, sorry, dot p. And p is just a normalized momentum. So that's the definition of the helicity. Right? If lambda is greater than 0, then we say that the particle is right-handed. Right? If lambda is smaller than 0, we say it is left-handed. Now remember not to confuse that with chirality. So if we have the visualization of a spin 1/2, right? So if we take a spin 1/2 particle, right? If it's traveling, let's say in this direction, if the spin vector s is in this direction, then we said that lambda is plus 1/2, and it's a right-handed. And if the spin is in the opposite direction, then lambda is minus 1/2, and we say it's a left-handed. Right. So helicity is not chirality. We discussed chirality as well. At least we mention it. It's another property of fermions. Now the helicity operator commutes with the Hamiltonian, which means that the helicity is conserved. Right. So one is that h and lambda is equal to 0, which means that helicity of a particle is conserved in time. But it is not Lorentz invariant. Right? If we have a massive particle, we can always move to a frame in which the particle travels in the opposite direction. And since the spin is something which is intrinsic, it doesn't change. But that means that the helicity is changed. So the helicity is not Lorentz invariant for massive particles. The exception is if the particle is massless, right? Because if it's massless, it travels at the speed of light. We cannot find a frame in which it moves in the opposite direction, right? So for a massless particle, helicity is both conserved in time and Lorentz invariant. But then it is coinciding with the chirality, right? For a massless particle, helicity is both conserved and Lorentz invariant. Now here comes a tweak, and we'll discuss that, I think, next week, right? The weak interaction does distinguish between left hand and right hand helicity states. So experimentally, it was observed that the W plus minus, the charge W bosons, they only couple to left-handed particles or right-handed antiparticles. Okay, this is not true in the other interactions. This is another unique feature of the weak interaction. Okay, so the weak interaction distinguishes between left-handed and right-handed states. So experimentally, W plus minus only couples to left-handed particles and right-handed antiparticles. Okay, there is something in nature that breaks the symmetry.
Right-handed and low and left-handed in terms of helicity or chirality?
Helicity. Talking about helicity here.
Okay.
Right. Another experimental fact is that neutrinos only exist in left-handed helicity states. And similarly, antineutrinos only exist in right-handed helicity states. So again, experimentally, right, neutrinos only exist in left-handed helicity states.
Are these two experimental observations independent of each other, or is it just that we couldn't measure one and so couldn't find the other, or vice versa?
No, because weak interactions don't only couple neutrinos. Weak interaction also couples, any fermions, including quarks and anti-quarks.
But neutrinos only couple weakly.
Yes, neutrinos only couple with weak interaction, but weak interaction, W bosons only couple with neutrinos.
So does that mean that there might theoretically be right-handed neutrinos, but because they can't couple through the weak interaction, because then we can't find that they can't be created, or maybe they can theoretically exist, but there's no process to create them.
They theoretically exist in supersymmetry. In supersymmetric models, they do exist, but in the framework of the standard model, we don't see them. We don't have any clue that they exist in the lab. I mean, we never saw them.
Could we have seen them if they were created in some process? What would they couple to in our detector system? What would they decay to?
I'll give you an example in a second. Okay, you could have them. Yes, at a certain energies, not at all energies. I'll give you an example in a few minutes. Okay.
I'm sorry. How would we know if there were right-handed neutrinos?
Well, that's what Ofek was asking. If there was a way.
So
there were processes. I'm going to give you that in example in a second.
Okay.
Actually, I think I'm going to give you to that in homework. That's why I'm doing it now. And antineutrinos only exist in right-handed helicity states. Okay. Now, this automatically means another experimental fact, and that is that the P and C, we haven't really spoke about C, as I won't mention. I know that I gave you the last problem set, number 5. You were supposed to prove something using the P. Many of you find a shortcut using the C, which is okay. So, but I meant to do it with the P because we haven't really spoke about the C.
Can I ask a quick question about the neutrinos? Sorry for interrupting.
Yeah, but can you wait? Can you wait 2 more minutes? I'll give you 2 examples, and then I'll answer these questions. Okay. I won't forget you. Okay. P, what does P do? P inverts the coordinate system, right? P inverts coordinate system. Right, just the spatial coordinates. A C transforms a particle into an antiparticle. So that means that P and C cannot conserve. I mean, this experimental results mean that the weak interaction does not conserve P and C, right? Because if I take a left-handed neutrino and a right-handed antineutrino, which do exist, and act on them with the P and C, right? And what we get is that P on neutrino, left-handed neutrino would give me a right-handed neutrino, and P on an anti-right-handed neutrino would give me an anti-left-handed neutrino, right? And the C on a left-handed neutrino would give me an anti-left-handed neutrino, and a C on an anti-right-handed neutrino give me a right-handed neutrino, right? Now we know that these guys exist. Right? But these guys do not exist in nature. Now that's true only for neutrinos, because the other leptons and all the other massive fermions do exist in both left and right-handed helicity states, which again makes sense because I can Lorentz transform. Right? It's just the neutrinos, which are presumably massless. They're not exactly massless, so they're very close to massless. Right? So other leptons, like E, mu, tau lepton, as well as massive fermions, exist in both left and right and helicity states. But of course, why did you do that? If we go to the ultra relativistic limit, right, in the limit where E is much greater than M, right, ultra relativistic, right, they can only exist as in the left-handed particle state or right-handed anti-particle state, similar to neutrino. And or right-handed anti-particle. Now I promised you an example. I'll give you an example and then I'll answer questions. I'm looking at the decay of a charged pion. Question, example. So pi plus goes to lepton, anti-lepton plus neutrino. That's a decay. Now we have really, there are 3 leptons, but there are 2 possibilities because of the masses, right? Since the mass of the tau lepton is greater than the mass of the pion, then we have that L can be either the electrons or the muon, right? Now remember that we derived the general expression for the two body decay, right? General expression for 2 body decay. Gamma goes P momentum over 8 pi m1 squared times the matrix element squared, right? This is the phase space. This is the amplitude. Yeah. Now, for both leptons, right, electron and muon, the matrix element is about the same, right? So for both E and mu, m is about the same. So the difference is that the mass of the muon, of course, is much greater than the mass of the electron, right? Which means that when we're producing an electron, it is produced with a much larger momentum, right? So when phi decays into anti-electron, right? The electron has much higher momentum. Right. So naively, when you look at this formula, right, one could anticipate that, I didn't expect that. One could expect that you get much more electrons than muons, right? Because the phase space is much larger, right? But that's all we're seeing. So experimentally, right? Right, 99.98% of the times, the decay goes into muon, right? L is equal to muon. And only 0.012% of the times, the decay is to L equal to E. Approximately, it's not exactly. Right. So why? Why is that happening? And then the answer is exactly what I just showed you, this spin analyticity of the particles. Right? So why is that? That's the question. And the answer is, again, look at the spin of the pion. So the pion has spin of 0. So that means that the spin of the two daughter particles, excuse me, right? They must be anti-aligned, right, in order to conserve the angular momentum. And you know the way to see that, right? You know, if you go to the pion's rest frame, pion, okay, so you have the neutrino and the L. Right. Now we know, I told you experimentally, that the neutrino must have must be left-handed, and that means that the anti-lepton must also be left-handed helicity state. So if I look at the helicity state, right? So the state, you know, helicity here, the spin has to be, it's left-handed, so the spin has to be opposite to the direction of the motion of the neutrino. And so also for the anti-lepton, it needs to be opposite. So neutrino is left-handed. Which means that the anti-lepton must be left-handed. Right. But here comes the thing, right? You said that the mass of the muon is much greater than the mass of the electron, and it's comparable to the mass of the pion. So mass of the pion is comparable to the mass of the muon, and they're both much greater than the mass of the electron. So that means what? If we go to the pion's rest frame, right, then the positron must be highly relativistic. So in the pion rest frame, right, the positron is highly relativistic. means that E is much greater than M, right? Which means I can treat it as being massless, approximately massless. But if it's approximately massless, that means that it can only exist in a right-handed helicity state. But we just say that the decay of the pion in the rest frame requires that the decay product is being in the left-hand state, the left-hand anti-lepton, right? That's why we rarely see it. On the other hand, if we're looking at the muon, right, mu plus, well, it's not relativistic. Right, again in the pion rest frame. Right, because it's not relativistic, it can exist in both helicity states. And that's why it makes it a dominant decay channel. That's known, technically, that's called helicity suppression. Okay, now I'll take your questions.
I have two.
Okay, go on.
First, could you say again why relativistic means right-handed? Could you mention that again?
It's an antiparticle. It's an antiparticle. Again, we have that the W plus minus only couples to left-handed particles and right-handed antiparticle. And experimentally, neutrinos, and for that sake, any massless particles, right? Relativistic massless particles, they only have a left-handed helicity. And then antineutrinos, which would be for that any massless particles, antineutrinos, so massless antiparticles would have a right-handed helicity state.
Okay, thank you. And the other question, why is there a chance that we will see it decay to an electron state, to a positron state? It appears like it shouldn't exist at all.
Well, because it's not exactly mass. It has some mass. There is some chance that it will be. If it was purely massless, then it would be zero. Right? It's a suppression.
Okay, I understand. Thank you.
I'm not convinced yet. This decay, this pion decay, happens through a doubly boson, right?
Yeah.
So I'm convinced a doubly boson can't couple to a right-handed neutrino.
Mm-hmm.
But that doesn't necessarily mean that there isn't a right-handed neutrino, just that the W doesn't interact with it.
Ah, that's a different story. If you have a new interaction, the standard model describes the interactions that we're observing in the lab and describes the particle. Remember, it's a question in philosophy more than anything else, right?
No, but that's
was constructed to describe the particles that we observe in nature and the interactions that we observe in nature between them.
Wait, but neutrinos were detected before the weak force was established via their missing mass or whatever, the missing momentum and energy, etc. So how can we be sure, or for example, I don't know, they can interact with gravity. How can we be so sure that they just don't interact with the forces we measure? For example, we don't measure gravity in CERN as much as I know.
Well, as I said, there are extensions to the standard. These are not part of the standard model. Within the framework of the standard model, we don't see that. There are extensions to the standard model. The most notable one would be the supersymmetry. And within some of the extensions, you do have right-handed neutrinos. But the fact is that so far there is no experimental evidence within all the experiments that we can do with all the energies that could have been reached, that were reached so far by all providers, you know, in CERN and in the US and everything. It was just never seen. If again, there are models which there are extensions to the standard model which states that at certain energies we will start seeing these particles. Right now, they're simply not here.
Perhaps what I'm asking is, do we not see any evidence for their existence, or do we see evidence that they do not exist? Which is similar, but not exactly the same, I think.
Okay, for the first, we don't have any evidence that they exist. Is there any evidence that they cannot exist? No, I don't think there is any evidence that they cannot exist, to the best of my knowledge.
So there is not direct evidence, but we are fine with the universe where they don't exist, and we describe what we see without needing them, right?
Yes, to the best of my knowledge, because I cannot tell you that I'm up to date with all the literature here.
No, sure.
But yeah.
Okay. Thanks.
I mentioned in the beginning, one of the first lectures, you know, there are still some open questions, mainly related to observations that are being done in cosmology, right, and in astronomy, not only, but mainly related to questions such as the nature of dark matter, dark energy, etc., that there is no answer to. You know, this is a first course in particle physics and in the standard model. So these are certainly things that are beyond the standard model. I mean, the standard model is excellent in describing what we're seeing in terms of the particles that have been detected and understanding them and understanding the different interactions between them. But it's not complete. I mentioned that, you know, it's the full honesty. We know that there is something out there that we do not understand. So that there is, you know, sometimes in the future, there will be a better theory, which would be able to account for, hopefully, you know, the expansion of the universe and the dark matter and other questions such as why we made of matter and not antimatter. All right. Any further questions? Shocked. I mentioned to you at the beginning of this, to give you some broad overview of some of the interesting things that are being done in the field of particle physics. As you can see, it's very deep, very broad. There are plenty of more things to do, and then, you know, in order to get them, we have to have at least 2 or 3 more courses. You know, you have to have a full course in quantum field theory so that you fully understand all the structure and the logic. I gave you some bits and pieces, but I cannot tell that you know, you're an expert in quantum field theory, and then with specific things that are specific for particle physicists and for the standard model. All right. Now the last thing I want to say about that, remember we made a table about type of things that are conserved. We made it quite, I don't know, a few weeks ago. We had a table about the conservation laws. Conservation. And I think now it's time to revise this table because we can add a few more things we didn't speak about back then when we made the table. So we had several symmetries and let's choose them. So for example, we had the, let's make a table. It's going to be a very good table. So we spoke about the strong, the electromagnetic, the neutral weak, and the charged weak. We have several entities such as the form momentum. So we know that the form momentum is conserved in the strong, electromagnetic, neutral, weak, and the charge weak, right? We know that the angular momentum, similarly, right, is conserved by all of these interactions, right? What about electromagnetic charge? What about it? Did I lose some of you? I thought there were more students around here. Are you with me, guys?
It cut out for a second.
What?
It started to lag for a second.
Somehow, suddenly I see only 4 people. There were more than that a few seconds ago. Okay, I don't know. What about the electromagnetic charge? Is it conserved by the strong force, a strong interaction?
Yes.
Yes. What about electromagnetic?
Yes.
Yes. Neutral, weak? Neutral, weak?
No.
Yes.
Yes. Charge, weak?
Yes.
Yes. What about the flavor? Is it conserved by the strong interaction?
Yes.
Yes. Electromagnetic?
Yes.
Yes. Neutral, weak?
No.
Yes. Neutral, weak? Neutral. Z. What about the strong? The charge weak, sorry?
No.
No. Very good. No, it's not conserved. What about the lepton number? Oh, what am I doing? What about the strong interaction?
Yes.
No, it's not relevant to the strong interaction. Electromagnetic one?
Yes.
Yeah, conserved leptonic number. Right, neutral weak? Z, does it conserve leptonic number?
No.
Yes. What
Yeah.
about the charge? There it is. What about leptonic family number? What about the strong interaction?
Irrelevant.
Irrelevant, very good. What about the electromagnetic?
Yes.
Yes. Neutral weak?
Yes.
Yes. Charge weak?
I think it doesn't. Not the generations. It does.
Yeah. The families. What about the baryon numbers?
Strong, yes.
Yeah, all of them, yes. What about the quark family number?
Strong in EM, yes.
Yeah.
And
What about the neutral weak?
Neutral weak.
What about the neutral weak? Z boson?
Z boson. Yes.
Yes. What about the charge weak?
No.
No. Very good. Right. CKM matrix. Now we can add up some new stuff. We already had that, I think. Now we can add a few more new stuff here. What about the parity? What about the strong?
Yes.
Yes. What about the electromagnetic?
Yes.
What about the neutral weak?
Neutral weak. Yes, the neutral one, yes.
No.
No.
Parity is conserved. So there are no right-handed neutrinos, right? What about the charge conjugation?
Same thing.
Same thing, very good. Conjugation. And this is the P, this is the C. Right. So the strong and the electromagnetic conserve them, but the weak one do not. What about the isospin? We discussed that as well. Total isospin. What about the strong interaction?
Yes.
Yeah. And the rest? The rest is not relevant. Isospin is a property of the strong interaction. What about the isospin projection?
The same.
Yeah. Well, isospin projection, I have to check out something here. Isospin projection. The I3. Right. It's the electromagnetic. Okay, I marked it as a yes because it's like it's but it's okay, that I have to check. So just leave it blank. It's definitely irrelevant for the week. This one I need to check. I marked it as a yes, but I need to check if this is the right thing. Okay. Now, where a few people disappeared, so it could be some connectivity issue with the university or something.
Probably, if they were both at the university and something happened there, then that would have knocked them both out.
Unbelievable.
I'm at the university and I'm connected.
You're not at the same building. I think they're in a different building, but I wish I knew what's happened there. Okay. So I want to speak about the isospin and addition of angular momentum. Right. So we discussed isospin, if you remember last time. Right. The derivation and the construction of the combined isospin state, these are all relied on the properties of addition of angular momentum, right? And the use of the Klebs-Jordan coefficient. Now, in principle, the Klebs-Jordan coefficient and the addition of angular momentum is something that you learn in a course in quantum mechanics. But I think it's in advanced quantum mechanics, which is given in the second semester of the third year. So I'm not sure that all of you have seen that.
Quantum mechanics.
Sorry?
Quantum mechanics 2.
Quantum mechanics 2, when is it learned?
First semester of the third year.
First semester of the third year. Okay, so it's good. Really? I need to be updated. So what is the material that is being taught in the first semester quantum mechanics?
I'm currently doing it, but we did identical particles, addition of angular momentum,
Okay, so that's what,
a bit of fine structure, stuff like that.
yeah, that is quantum mechanics too. Okay, I thought it's learned in the second semester. Okay, it's quite good that you learned it in the first semester. So I had very briefly a slight not review really, just some demonstrations of how to use that, just to make sure that everybody is aligned with me. Right, so a general, so let's do it. It won't take more than a few minutes, and then we'll resume back to the main class. So Okay, help me. So we said that when we have a general state, general eigenstate of the angular momentum operator J, it is being described by two quantum numbers, right, which are denoted by J and M. Right, this is a general eigenstate of the angular momentum operator. J, right? So J, right, is the eigenvalue of the operator J squared, right? Jx squared plus Jy squared plus Jz squared. And M is the eigenvalue of the Z component of J. Eigenvalue of Jz. Close series. Thank you. Sorry for that. So the question is, what happens when trying to combine two such states? Right. Then the resulting state is describes the total system. You know, is an eigenstate of the operator J. So when combining two such states, right? Then we have an eigenvalue or eigenstate of the operator. Everything okay? J is J1 plus J2. So this is described as a linear combination. It's a linear combination. It can be described as a linear combination. All right, so what? Close series.
Sorry, there's nothing to repeat.
I know. J1, M1, and J2, M2. Right, it's just sum. Where J goes from. What's going on here? 3. Seconds. Carl, are you with me?
We're with you, but your tablet seems to.
Something wrong in the tablet. Not sure what it is. Close series. Okay, I'm not sure what it is. Sorry for that. J goes from minus, doesn't go anywhere, minus J1 plus J2. To J1 plus J2 of C, J, J1, J2, M, M1, M2, and JM. Right, you know that. Sorry for the time it took me to actually rewrite it. And this coefficient, right? C, J, J1, J2, M, M1, M2, These are the Klebsch-Jordan. Klebsch-Gordon coefficients. All right. Now, there's no need to derive them because they have been derived and you can find them in any table, right? And you just need to use them for a given combination of J1, J2, M1, and M2, right? So for any combination, right, of J1, J2, M1, and M2, right, you can find and use the table to find them, right? And always we have that M is M1 plus M2, right? So it's easy to find such a table. Let's go, so actually found a table. So I'm going to use a table to, you know, let's try to compose the isospin state. So use the table to compose the isospin state of the pi plus the proton, pi 0 and the proton, pi plus and the neutron, pi 0 and the neutron, pi minus and the proton, and pi minus and a neutron. So A, B, C, D, E, F. Right? I think you had it in the problem set. Did I give it to you in the problem set? Can't remember at the moment.
Possibly.
Possibly, yeah. So let's see how it's being done. It's supposed to hand them today, right? Or tomorrow?
Tomorrow.
Tomorrow. Okay, so I'm going to help you partially. Here's a nice thing. I just downloaded it from the web. Just go to the PDG and you find the Klebsch-Jordan. So that's how it looks like. So let's look, for example, at the pi plus and the proton. So pi plus and a proton, right? So we know that the pi plus, right, is a 1, 1. And the proton is half, half, right? So we have I equal to 1 multiplied by I equal to half. Right? So we look at the table, right? This is the relevant table, right? So we have the coefficient, right? We have the Jm and the initial states, right? The M1 and M2. So here we have, first we look at the relevant table, which is of course this table, right? 1 times half. And we have plus 1. So M1 and M2, right, is 1 and 1 plus 1 and 1/2. It's only this one, right? And the J and M is only one option. 3, 2, and 3, 2. And so the coefficient is square root of 1. Right? So we have the combination of M1 is 1, M2 is 1/2, right? And then we get that C must be square root of 1. And that multiplies the quantum state with J equal 3/2 and M equal 3/2. So we have that the pi plus and P with 3/2 and then 3/2. Right? Yeah?
Yes.
Good. So let's look at B. The pi 0 and the P. So now we have the pi 0, right? Is a 1, 0. The P is 1/2. So again, we have I equal 1 multiplied by I equal 1/2. So now we have a combination. Pi 0 is, what did I do? Pi 0 is 1/2. Now we have a combination of M1 equals 0 and M2 equal 1/2. So we're still looking at this table, right? M1 is equal to 0. M2 is equal to 1/2. Is this one. Right? And then we have that the J1 and J2, what they're given here, and the coefficients that we're looking at are square root of 2/3 and square root of minus 1/3. Right?
Yes.
So we have C of square root of 2/3, which multiplies the 3/2 and 1/2. And then we have C of minus square root of 1/3 multiplies the 1/2 and 1/2. So overall, we have that the pi 0 and P state, you can write it down as square root of 2/3, 3/2 and 1/2, minus square root of 1/3 of 1/2 and 1/2. Like another example, right? So if you look at the pi plus and the n, right? So we have that the pi plus is 1, 1, n is 1/2 minus 1/2. So again, we have I equal to 1 multiplied by I equal 1/2. So we have M1 equals 0. Did I do that? Sorry, M1 is equal to 1. That's because it's a typo in my, I have a typo in my notes. And M2 is equal minus 1/2. Which means that we're looking at this table, that's fine. But then of course we have now that M1 is 1, 2 is 1/2. So the coefficient of interest with these guys, right? Which will correspond for the JM of 3/2 and 1/2 and 1/2 and 1/2. we have C is square root of 1/3, which multiplies the 3/2 and 1/2. And then we have C equal to square root of 2/3, which multiplies the 1/2 and 1/2. So overall, we have multiplied plus an n, that is square root of 1/3, 3/2 and 1/2, plus square root of 2/3, 1/2, 1/2. Okay, I think that's enough. Solve you half of your problem set. Is that clear what I'm doing here?
Yes.
Good. Did you do this before?
QM.
What?
In quantum mechanics.
Sorry, I did not understand what you said.
In quantum mechanics.
In quantum mechanics, yes. Okay, so that was a little bit of a waste of time, maybe, but maybe not that much. You know what? Since we're running out of time, we lost the class roughly. Let's do a final example. Let's not look at something which you already had. So let's look at 3/2 multiplied by 1 minus 1 state. So here we have I1 is 3/2 multiplied by I, which is 1. So let's look at the relevant table. So now we have a different table. So 3/2 times 1. It's this table here that we care about. All right, and then we said that M1, let's say, M1 is 3/2 and M2 is minus 1. So M1 is 3/2 and M2 is minus 1. We have it here, right? And the coefficient that we have right here for this combination of J and M, right? 1/10, 2/5, and 1/2. So overall, we have like let's write down the final answer. 3/2 multiplies by 1 minus 1 is square root of 4 over 10. And then we have the 5/2, 1/2 plus square root of 2/5, 3/2 and 1/2 plus square root half times half. Okay, it should be quite straightforward. The rest should be easy. Just practice using the Clebsch-Jordan tables. I did not derive, you know, the theory behind it. It's just using the ladder operator for angular momentum, which you're supposed to do in the quantum mechanics course. I guess the main contribution is to show that this has a lot of applications in particle physics as well, not just in non-relativistic quantum mechanics. Okay, so as I somehow anticipated, these tutorials, which I thought were supposed to take 1 hour, they take 2 hours at the end. But again, that's fine as long as it's meaningful for you. So I will just, so there's no point in continue on now with the quantum chromodynamics, but we will do it next week. So I still want to cover with you in the next 3 weeks that are left of the semester. I want to do the quantum chromodynamics, I want to do the weak interactions, and I want to do the Higgs mechanism and the spontaneous symmetry breaking to describe how particles gain their masses. So it's quite cool stuff. And that's what I have to say. So to say, I'm going to give you another problem set, so to keep you busy towards the end of the semester. And that's it. I can just wish you a safe weekend and a healthy weekend and enjoyable weekend and whatever.
Thank you. You too.
Any further questions or comments before we leave?
Happy New Year, everyone.
Happy New Year. Yeah. well, you cannot really celebrate. Those who want to celebrate here, it's pretty much impossible. But let's hope that the 2021 would be a better year than 2020 for all of us.
תודה רבה.
Thank you.
All right. So what do I do?
Goodbye.
Stop sharing. Stop recording.